Hello, everyone. Welcome to pre-lecture 18. In this lecture, we're going to be talking all about acid-base titrations. So you are already familiar with what a titration is, thanks to what we did in lab last week, or rather, I guess, the week before break. But why do we care about titrations? They're a method to determine the amount or concentration of an unknown. They can also, as we did last week, be used to determine something like a molecular weight. They're performed by adding a stoichiometric amount of titrant to analyte. And so our titrant tends to be a strong acid or a strong base. And then our analyte tends to be something that is unknown, maybe, but or an unknown concentration at least. And it is used typically a weak acid or weak base. Okay. We titrate until we reach an equivalence point, which is typically determined through use of an indicator. Okay. Again, you can do a number of different types of titrations, but in our case, we're going to be doing acid-base chemistry. So we're always going to use at least a strong acid or a strong base to determine our analyte. Okay. Something that we touched on in lab, but I want to talk a little bit more about here are indicators. And so the one that we used in lab is phenolphthalein, that is clear at acidic pHs and bright pink at our more basic pHs. And there are a number of indicators out there. We're going to actually be using quite a few in lab this week, and they will change color depending on whether they are protonated or deprotonated. And so all this is to say, an indicator is a weak acid base pair in itself. And within it, so in this example here, we have an indicator that would be blue when it's protonated and red when it's deprotonated. And typically that transition between blue to red, or whatever our starting color is and our ending color is, happens within 1 pH unit. And so that transition will typically happen within 1 pKa unit of our acid. Okay. And so a quick example is, what color would the solution be if our pH was equal to our pKa in the indicator above? So take a moment to think about that and do the answer now. So hopefully you could get that it would be purple. The reason that is, if we mix blue with red, we get purple. And so if pH was equal to pKa, we would have an equal amount of our protonated and deprotonated indicator, meaning that we would have approximately equal amounts of blue and red, meaning we should see purple with our eyes, right? So these are a number of different indicators that are out there. We have basically, I think we'll use 6 of these in lab this week, but you can see all the different kinds of colors you can transition to depending on what sort of indicator you're using. And you can even see some of them, like alizarin has multiple color changes across a range. Okay, so want to talk a little bit more about the anatomy of a titration curve. Typically, our most important point on it is the equivalence point. And that is technically defined as the number of added moles of titrant being equal to the moles of analyte of the original solution. And so if we have a strong acid and a strong base, that is when say we add a strong acid to a strong base, then at our equivalence point, our pH would be equal to 7. If we were adding a strong acid to a weak base, then at our equivalence point, our pH would be less than 7. We'll talk a little bit more about why that is in this video and in class. And then if we're adding a strong base to a weak acid, then at our equivalence point, our pH will be greater than 7, or basic, right? So the other big important point that we measured in lab the week before spring break was the half equivalence point. And this is where the number of moles of titrant that is added is equal to half the moles of analyte in the original solution. And so at this point, it is, of course, important to remember that our weak base and conjugate acid are equal, or weak acid and conjugate base are equal. And the big key here is that this is where our pH is equal to our pKa. And so it can be a very useful way to, if we're able to reach the half equivalence point, it can be a very useful way to determine what our pKa for a given acid-base pair is. Okay. So looking at this titration curve, is this titrant an acid or a base? Is the analyte an acid or a base? Is the analyte strong or weak? So take a moment, think about this, and then I will put the answer up here. So this would be an example of a strong acid and a strong base reacting. The reason we know that, and hopefully you got that our titrant is going to be our NaOH and our analyte is going to be HCl. The reason we know our analyte is HCl is because we're starting at a low pH or an acidic pH, right? Then as we add in our NaOH, volume of NaOH added, you can see our pH start to go up until we start to get close to our equivalence point. With a strong acid and strong base, you reach the equivalent point very rapidly. You can see that our equivalent point is at a pH of 7. And so we know that that would be our equivalence point because we're at a pH 7. That also tells us that we're using both a strong acid and a strong base. Okay, and then after the equivalence point, we end up with more basic pHs when we have an excess of sodium hydroxide. Okay, and sorry, that was everything I just went through. Just forgot to put that part up there. Okay, all right. What about this one? Think about, is the titrant an acid or a base? Is the analyte an acid or a base? Or is the analyte strong or weak? So take a minute, think to yourself. See if you can figure it out. So an example of this is going to be, our analyte is going to be a weak acid. Our titrant is going to be a strong base. I'm just using sodium hydroxide as an example there. A minus could be our conjugate base. The reason I would know this, if we can look at the titration curve in different areas, we have our initial pH that is acidic, right? pH around 2.1 or so. And so we know that that's going to be a weak acid, or at least an acid. We don't necessarily know it'll be weak yet. Before we reach our equivalence point, we're in what we would call the buffer range. And that's because we can use the Henderson-Hasselbalch equation to calculate the pH in this first section here. And then if we look, our part with the steepest slope is going to be right here at the equivalence point, and that is also going to be where our pH is a little above 8, meaning that we are starting with a weak acid, and once we have added the same number of moles of NaOH, all we have left is our conjugate base at the equivalence point, right? Because then we have sodium A minus, and that's going to be acting as base, and so it will create a basic pH. Okay. After the equivalence point, the way we would find our pH is determining the excess amount of hydroxide that's left. And so we're going to go through an example like this in class on our worksheet, actually calculate all of the different parts. Okay. All right. Looking at this curve, same questions. Is the titrant an acid or a base? Is the analyte an acid or a base? Is the analyte strong or weak? And we have the starting point, half equivalence point, and equivalence point here labeled. And hopefully you were able to get it. This would be an example of a weak base, ammonia, being titrated with a strong acid, HCl. The way we would know that is our initial pH is going to be basic, right? Somewhere around 11, 11.12. And then our equivalence point is going to be acidic, right? So our pH is 5.26, which is acidic, meaning that this would be a weak base titrated with a strong acid. Okay. Right. What about this one? Tricky. We have multiple equivalence points. What do you think? Is our titrant a weak acid or base? Is the analyte an acid or a base? Is the analyte strong or weak? So hopefully you were able to get. We're starting with a weak acid here. And the trick here, the reason we have two kind of plateaus, is because this is a polyprotic acid. So if we start with the form of our polyprotic acid where we have H2A, we start adding in our titrant, our strong base, we reach our first equivalence point, Then we keep going, we level off for a little bit, and then we start to reach our second equivalence point as we have basically our second deprotonation step. Okay, so hopefully that makes some amount of sense. That's all for right now with titration station, but we're going to do a lot of the math behind these titrations in class on Thursday. So come ready to do lots of calculations. Hope you have a good rest of your day and see you soon.